Okay, so what we'll do next is we'll go through a few problems that I got out of the end of chapter 8 in your book, and we'll use these as practice problems. So, like with the previous chapter, I will kind of tell you what the problem is, give you a second to pause the video and try it on your own, and then we'll go over it right after that. So, for our first example, we're asked to predict the molecular shape of SbF5 antimony pentafluoride. So for any of these examples, we need to come up with the correct Lewis structure first. So antimony on the periodic table, Sb, if you look at its position, it's in the same column as nitrogen, so it's going to have 5 valence electrons. And then, of course, fluorine is a halogen, so it's going to have 7 valence electrons, and there are 5 fluorine atoms. So we have 5 atoms times 7 electrons each, and it's neutral, so we don't need to add or subtract any electrons from that. 5 times 7 is 35. Add 5 to that, we get 40 electrons. So that's how many electrons we need to place in this Lewis dot structure that we can then use to predict the shape. Fluorine's never the central atom, so we're going to start step 2 by putting antimony there in the middle, and we can attach our 5 fluorine atoms to that. And I happen to already know what the correct shape of this molecule is going to be, so I'm going to draw it a little bit presumptuously so that when we get to the point where we predict the shape, it'll be a little bit clearer exactly what this looks like. So you can see the wedge and dash bonds indicating one of these fluorine atoms is coming out of the screen, the other one is pointing behind the screen. So that used up 5 bonding pairs for those 5 single bonds. So we have at this point 40 minus 5 times 2 is 10 is 30 electrons remaining. The next step, of course, is going to be to place those electrons around the fluorine atoms to complete their octets. We have 5 fluorines, and they all need 6 more electrons to do that. So that's exactly going to consume all 30 of these electrons. So we won't be putting down any electrons on our antimony atom. We won't have any left at that point. So putting 3 lone pairs on each of our fluorines. There we go. So that's our Lewis structure. We've placed all the electrons. Our antimony in the center actually has 10 electrons around it, so we definitely don't need to turn any of those lone pairs into double or triple bonds or anything like that. So we're going to work from this right here. Now in terms of charge clouds, we have 5 fluorine atoms and no lone pairs. So that's 5 charge clouds in total. And when all 5 of those charge clouds are atoms, in this case fluorine atoms, we're going to have a trigonal bipyramidal molecular geometry. So if I just go back a few slides, we can see right here, if we have 5 charge clouds and none of those are lone pairs, we have a trigonal bipyramidal geometry. Okay, so that is antimony pentafluoride. Let me go ahead and erase this so that we can come back to this later. And we'll move on to the next example, which is going to be to predict the shape of this ion here, which has formula IF4+, so it's got a charge on it, which you'll need to account for. So again, go ahead and pause the video, try this on your own, and then we'll come back and work through this together. Okay, so hopefully you've tried this on your own. Both iodine and fluorine are halogens, so they all have 7 electrons. So we have 7 from our 1 iodine and 7 from our 4 fluorines, so 4 times 7. And then we have a +1 charge, so we need to subtract 1 from this. Remember, electrons are negatively charged, so a positive charge means we have fewer electrons. 4 times 7 is 28. Add 7 to that, we get 35. Minus 1, we get 34 electrons to place in this. Fluorine's never at the center of the molecule, and iodine is much less electronegative than it is, so we'll go ahead and put iodine in the center. And we're going to put our 4 fluorine atoms around this as well. And again, I already know what the shape's going to be like, so I'm going to draw it in a more suggestive way. And we used 4 bonds, or 8 electrons to do that, so we have, let's see, that's going to be 26 electrons left at this stage. And we need to next fill out the octets of our fluorines, which takes 3 lone pairs per atom. So that's 6 electrons times 4. It's going to use 24. So after we put those down, we're going to have 2 electrons left, so we'll go ahead and place those. And we have 2 electrons left, so no place to put those except on our iodine atom, so we'll give our central atom a lone pair here. Go ahead and circle that just to make it a little bit more clear. So how many charge clouds do we have here? We have 4 atoms, and 1 lone pair. So that's going to be 4 and 1 is 5 charge clouds. And you might remember, this one's actually kind of easy to remember just because the name's so weird, that if we have 5 charge clouds and 4 of those are atoms and only 1 of them is a lone pair, this is going to be a seesaw shape. So seesaw. And if we go back a couple of slides, you can see, in fact, if we have 5 charge clouds and 4 of those are atoms, that we have, in fact, a seesaw shape there. So if we come back to this, I know it only asked us in the problem I got out of the book to predict the shape, but we can go into a little bit more detail for practice. So if we were asked to predict the bond angles here, this has 5 charge clouds, so remember with those you have 2 different types of bond angles based on axial and equatorial positions. So this fluorine here and this one here are axial, and the other 2 are going to be equatorial. So we'll go ahead and label them. So there's 2 types of bond angles to consider. One is between an axial and an equatorial position, and the other is between 2 equatorial positions. So this angle here, from axial to equatorial, under ideal circumstances, that would be 90 degrees. And between 2 equatorial positions, ideally that would be 120 degrees. Now if we had 5 atoms for our charge clouds that were all the same size, then those angles would be exact. However, One of these charged clouds is a lone pair, which means it's going to contract some of these bond angles. So this angle here is probably going to be a little bit less than 90, and this one will be a little bit less than 120 degrees. But the bond angles will be pretty close to those two values. Okay, so that's that example. Let's look at another one. This one is for the nitrate ion, NO3-. You hopefully remember that from your polyatomic ion chart. What I'm going to do, again, is you can try this on your own, pause, and then start the video back up whenever you're done. So for the nitrate ion, we'll go ahead and look at this example. We have a nitrogen and 3 oxygens. Nitrogen has 5 valence electrons. Our oxygens are going to have 6 each, and there's 3 of them. So we're going to have 3 oxygens with 6 electrons each. Remember, we're only considering valence electrons here. And we're going to add 1 electron because of the negative charge here. So 3 times 6 is 18, add 5 to that is 23, and then add 1 to that, we get 24 electrons to place. Now, this example is slightly interesting because we're actually going to have 3 different resonance forms. And since we're going to have 3 resonance forms, I'll go ahead and show you what you should end up with. So we have a nitrogen in the middle and 3 oxygens. And to complete the octet of the nitrogen, you will end up needing to use a lone pair on one of these oxygens to form a double bond. And the 3 resonance forms just differ in terms of where that double bond is. And wherever you have a double bond, of course, we've taken a lone pair from that oxygen and turned it into a bonding pair. So the double bonded oxygen will have 2 lone pairs, the singly bonded oxygens will have 3, and the other 2 resonance forms are basically just the same, but with the nitrogen-oxygen double bond in one of the other positions. So this will be good practice just to kind of go over resonance. It is an important concept, even though it's not strictly necessary for this problem, as we'll see in a minute. So those are our 3 resonance forms, and since this is an ion, this is supposed to be in brackets, and we're going to indicate the charge, which means I guess I probably should have done that for this previous example as well. So just for completeness, we'll go back and do that. Anyway, so these are our 3 resonance forms. Now, to predict the shape, we just need to know what's going on around our central atom, which is nitrogen. And regardless of the resonance form, our nitrogen atom always has 3 charge clouds around it, and those 3 charge clouds are always 3 different oxygens. Remember, it doesn't matter how many bonds there are between any of the atoms, we're just counting the number of separate atoms attached to that central atom. And in no cases does the nitrogen have a lone pair. There's not enough electrons for that when you go through the steps. So when we have 3 charge clouds, and they're all atoms, this is going to be trigonal planar. So this is essentially a flat triangle shape. And based on that, all of our bond angles should be 120 degrees. And since we have 3 identical atoms, all of the bond angles will in fact be exactly 120 degrees apart. So that's the shape of our nitrate ion.